Yeah, chapter 6. So, breaking bonds. Delta H. Okay, what's delta H? Enthalpy, right? Okay, so delta H is enthalpy. If you break a bond, what is delta H? Positive or negative? Positive. Why is that? You have, yeah. Why do bonds form? It's not a trick question. Why do any bonds form? It's more stable. That's the answer to everything. Well, not everything, but because we started doing kinetics in this, in organic. And 1B, not everything was more stable because kinetics sometimes is just faster, right? But generally speaking, things are more stable, and that allows them to form. So bonds form, they must be more stable in the separate atoms. The more like sciencey answer is it's molecular orbitals, and as molecular orbitals, atomic orbitals come together, it creates a bonding molecular orbital, an anti-bonding molecular orbital. And what do the electrons do when that happens? You guys remember? They do spread out, but they spin. They're always spinning, sorry. At least we're getting a little interaction, okay, so I'm appreciative of that. They spread out around the molecule, but they go into the bonding molecular orbital, right? So that's the lower energy molecular orbital. That's more stable. So in order to break a bond, you've got to push the electrons out of the bonding molecular orbital to break the bond, okay? So if you break a bond, you're going to have to put energy into it. If you're going to make bonds, then this is going to be negative. It's the opposite. It's an exothermic process. So what favors spontaneous? Negative. Definitely delta H being negative favors a spontaneous reaction. Why is that? That's your problem. Why is that? Because,
I thought it was the sun.
the sun. Yeah, we'll go back to the sun. Yeah, because it's the sun. I got a great song about that for my kids, but anyway. Okay, so, yeah. Favors a spontaneous reaction because when you make bonds, it's more stable. Okay. Now we talked about entropy. Delta S. So, if I don't want to put it on that kind of way. I'll do it like this. Delta S. If delta S is positive, what does that mean again? Not disorder. More probability, more chance, more choices, more stuff, more ways. Yeah, more ways to. I got a big. Here's an interesting phenomenon. This happens to people. I had a small house and I got a big house, and guess what I did with my stuff? I got more stuff, and I put it everywhere in my house, so then I had to get more stuff. Right? It's availability of states. I had more states available to me. I used them all. What if delta S is negative? What does that mean? Less stuff, less ways to arrange your stuff. Right? Probability. It's not just less stuff, but it's less ways to arrange your stuff. So, which one favors a spontaneous reaction? Yeah. You ever clean your room, right? No? See? That's why this is... Because when you clean your room, you take your stuff that's all spread out and you put it into fewer available states. It takes energy to do that. That's why molecules don't like doing it. They take their energy and they put it into fewer available states. They don't like that. They want to spread that energy out. That's why they like more available states. That's why that's favored. So if delta S is positive, this favors a spontaneous reaction. And delta S negative? What's the weird word? We don't use spontaneous. It's non-spontaneous. Yes. favors, I don't know how you favor something not happening, but favors a non-spontaneous reaction?
Well, something is happening. Just reverse.
Yeah, that's right. Yeah, what it actually favors is the reverse of that
Exactly.
reaction. So, I remember we talked about how the entropy of the universe is always going up. Okay, so a couple of interesting situations. When delta H is positive and delta H is negative and delta S is positive, these will always be, magic word, spontaneous, not more stable, but nice try. And if delta H is positive and delta S is negative, they're always non-spontaneous, which means they're always spontaneous in reverse. I wanted to get that in there before you did. So. I want to just get that in there before you said it, because it's the truth.
Reverse spontaneous.
Yeah, reverse spontaneous. Okay, good. Okay, so if delta H is positive and delta S is positive, or delta H is negative, let me write. I'm running out of room here. Delta H is positive and delta S is positive, or delta H is negative and delta S is negative, then whether or not it's spontaneous depends on temperature. Okay? So remember the equation for free energy. Delta G is equal to delta H minus T delta S. At high temperature, one of these two terms is going to be more important. Which term? The one that has temperature in it. Okay, I'm sorry. This one. So you'll notice that this favors spontaneous, right? But this doesn't. And you'll notice this one favors spontaneous, but this what doesn't. So in the high temperature region, at high temperature, what do we do here? High temp. This term's more important. So at low temperature, that's more important. At high temperature, that's more important. So at low temperature, you would expect it to be non-spontaneous because delta H is positive. And at high temperature, you expect it to be spontaneous because delta S is positive, which, remember, this is a positive. There's a negative sign here, so that's what makes delta G negative. The reverse is true for this one. At low temperature, you expect this to be what? Spontaneous, because delta H is negative. This term's not important, or less important. And then at high temperature, this term's less important. But the bottom one's more important, and as a result, it's non-spontaneous at high temperature. So this one favors spontaneous, and this is non-spontaneous. And it's all dependent on what the temperature is, and then the balance between delta H and delta S. And if you remember this equation, which you don't really have to know, but I just want to throw it out there just for fun. When delta G is equal to 0, that's equilibrium, okay? Then you could solve this for T, and T is equal to delta H divided by delta S. And that tells you the temperature where it switches from either being non-spontaneous to spontaneous or spontaneous to non-spontaneous. That gives you the actual temperature if you calculate it. And it's an estimate, but it's not a bad estimate. Okay, so let's take a look at this reaction. I have A and B. They're bonded together, and they go to A plus B. How? I have no idea. Delta H is, just looking at it, it's pos negative. Negapos?
It's at equilibrium.
That won't hurt enough. Positive. I get positive? Positive?
Positive.
Positive. Are you sure?
Breaking bonds.
I'm positive.
Yeah.
Yeah, you're breaking a bond, right? So you're breaking a bond here from A to B to go to A plus B. You're breaking a bond, so delta H is positive. Ew. And then, what's delta S? Just based on what you see. You sure? I'm positive. I give you all these opportunities for stupid jokes. What does that mean? Look at this, look at this. What does this mean? Describe what that means. Depends on temperature because the signs are the same. At low temperature, it's non-spontaneous because you got to break a bond and that takes energy. And at high temperature, it's spontaneous because you get more entropy out of the system by splitting those two up. Okay. So even though you know there's nothing really written there that you can interpret other than there's one bond that broke and it's 1 to 2, you could actually predict for reactions that look like this, where you're breaking bonds and then making more entropy, how it's going to behave, right, when you change temperature. What about this one? What's delta H? Positive, right? Because you're breaking one bond. So when we do bond energy calculations, we actually look at individual bonds and how much energy it takes to break them. So since delta H is positive, what's that mean? Same thing it means over there, but what does it mean again? Non-spontaneous at least low temperature, right? And then delta S, you have to interpret that. Positive or negative? Same. Okay, so what does delta S mean if it's positive?
Increasing in entropy
Increasing
as more available states.
More available states.
Right.
Right?
Acyclic.
So let's say I'm cyclic. I'm
You're
cyclic.
stuck.
And I want to do this.
Yeah.
So I could do that, right? But, and I'm not a dancer. If I was a dancer, I could do this really good. But I can't do this, right? I can't do this. So available states has to do with how you can arrange your energy. When your ends are tied together like this, your cyclic molecule, and you try to move this side independently of this side, you can't. Delta S is positive because you're going from a cyclic compound to an open chain compound. So structure will tell us something about entropy as well. And if you look at the structure, if it has more available states, there's more way to arrange the energy. Okay, so let's see if there's anything. So if these reactions were slightly endothermic, delta S for both of them is positive. And as a result, at high temperature, they're spontaneous. At low temperatures, they're non-spontaneous. Okay. Hey. Let's take a look at this reaction. This is known as the Diels-Alder reaction. And when you get to it, I'm just going to warn you, this is one of my favorite reactions because it's if a reaction could be beautiful, this is a beautiful reaction. It's like a dance where pieces all move together. It all happens. Yeah, anyway, sorry. Was that a little creepy?
Yes.
Whatever.
I've never heard anybody talk about molecules like that.
Yeah, well, I married a chemist too, so takes one to know one kind of thing. Of course, she hated OChem, but that doesn't matter. I still love my wife, regardless of that minor defect.
We're all defective.
Yeah. So, what do you think delta S is?
Negative.
Negative. All right. So this is my Diels-Alder reaction. Delta S is negative.
How do you spell Diels-Alder reaction?
Oh. It's been a long time since I spelled it. Deals? No. Deals. No, that's not it. Deals.
No, I'm pretty sure if you just type it in, it'll link it into Google with your best guess.
Yeah, I know. I keep wanting to put an H in there, but I don't think there is a H in there. Deals, alder. Reaction. And I'm second guessing myself on the I and the E because it's German. But and if you say E or if you say I, it changes the order of the E and the I, and I forgot which way it goes. I had German. I got it right? Okay, good.
You check score, you.
Thank you. So that's the Diels-Alder reaction. Delta S is negative. Now, what is delta H? So what are you doing? So what are you breaking over here, and what are you making when you get to here? Break 2 pi bonds, right?
Making 2 sigma bonds.
Make 2 sigmas. Okay, now you guys remember pi bonds, sigma bonds. Which is stronger?
Sigma.
Sigma. And a double bond stronger because it's a sigma and pi, both, right? So that's one of the things people forget. So which bonds are stronger? Here? On the right or the left? The right. So takes energy to break these. You're going to get energy when you make these. So exothermic or endothermic? Exothermic, because when you make stronger bonds, it's more stable, so it's lower in energy. Okay? So you're making bonds that are more stable than you're breaking, and it's the same number of each, so this is also negative. Okay, so what does that mean about this reaction? Temperature dependent. High temperature, non-spontaneous. Good. So one of the things that we do when we talk about Gibbs free energy is we write these reaction as energy diagrams. You guys all remember energy diagrams, it's your favorite thing ever. This is the reaction coordinate, and it's kind of like time, except for it's not really time. It's just like the progress of a reaction. So it's like, when you do one of those things when you're a kid and you have numbers 1 through whatever, and you just connect lines, and all of a sudden you have like a tree. Right? That's what it is. It's like you're just following the progress of your pencil, and you end up with this. This is not necessarily linear time. Those lines aren't all the same in those little drawings, right? Okay, so free energy, delta G. If you go from high free energy to low free energy, we say this is an exergonic reaction. It's like exothermic, except for it's lower in free energy, which is the combination of delta H and delta S. Okay. When delta G is lower in energy, we call that an exergonic reaction, and these are the spontaneous reactions because you're going to overall lower energy. Okay. I'm compressing a few things. What's this?
Activation.
That's the activation energy. Okay, so when you go on into your biochemistry class in the future, they'll show you a diagram like this, and most likely it'll be G, free energy, on this axis. And this is your activation energy. It's the free energy of activation, and they usually call it this. Your book doesn't do this yet. That's your free energy of activation. So, what? So what? Free energy of activation. Who cares about it? What does it mean for us?
That's how much energy do you need before it goes over the top.
Yeah, it's the energy required by a molecule, right, in order to create the product. It's the hurdle it has to go over. Okay? Why is this important? Because it turns out, like when you die, what happens to your body? just decomposes. If that activation energy barrier was really low, we'd have a lot of problems, right? Because your body would just be like, well, actually mine is, but your body would be decomposing at a very fast rate if that activation energy wasn't pretty high. You know the whole thing about spontaneous human combustion? Right, that's a very exothermic reaction. I don't believe that it actually happens, just so you know. But it's a very exothermic reaction, but it doesn't, and you know, burning is a spontaneous reaction. You can light things on fire and they burn. The reason we don't run around like matches all the time, the activation energy is really high, right? If it was really low, we'd all just burst into flame and that would be it. By the way, you know what the two things that are usually associated with spontaneous human combustion are? Smoking's one of them. Alcohol is the other. And you know where they find these people a lot of times? On the toilet. So usually they find their legs. So, just saying. Smoke on the toilet. Drunk. Drop the cigarette in your underwear. I'm just saying, guys, smoking's bad for you. Okay, so, you know, for early mornings, you have to have something to wake people up. So. I didn't tell the other class that story. I don't think they can handle it. Okay, so. Yeah.
Because it's morning, we're not going to remember that.
Yeah, well, you'll remember it, but then you'll be like, now I have to listen to the lecture because I have to listen. Or he's going to tell me another one of these stories about people burning up on the toilet. Yeah. Okay, so delta G doesn't tell us anything about the rate, though. The normal delta G, not delta G key. Delta G doesn't tell us anything about rate. What does it tell us about? You guys remember? What?
Energy required.
Kinda. Free energy, so it's a combination delta. But if you had delta G, what could you calculate from that? You guys remember? Not how quickly. That's this, the activation energy.
Oh, yeah, equilibrium.
It tells us about equilibrium. All right. So if delta G is negative, we say, oh, it's a spontaneous reaction. So the reaction is going to go to the right, and it's going to produce products. So we would say if delta G was negative, it's a product-favored reaction because it's going to tell us how far to the right. Delta G tells us essentially how far to the right it will go. If you remember the equation, it's this one. Oh, actually, that we changed it to K. It starts out as Q, but it ends up being K. If this is a really big number, big exponentially large number, then this will be negative. Right? That kind of thing. So the size of delta G, the standard free energy, tells us how product favored or how reactant favored a reaction will be. Now, if this is product favored, what does an energy diagram look like for a reactant favored situation? It's the opposite. The reactants are low in free energy and the products are high in free energy. Right? So it looks like this. And we would call this an endergonic reaction. And at equilibrium, we would expect to find more reactants in the mixture than we would find products. Okay, good. Let me do something real quick. So this tells us how much, this energy difference tells us how much material we'll find at equilibrium. Now those values do depend on concentrations. Delta G is for the standard free energy of formation. If you remember what standard is, it's 1 molar, 1 atmosphere, all those good things. And about 25 degrees Celsius, there's not actually a standard temperature for all this stuff. Now, in a reaction in organic chemistry, do you ever expect your reaction to go to completion? they're almost always some sort of equilibrium. And how far they go towards completion, that means 100% conversion, depends on delta G. Now, why is that? You guys know? Well, you guys remember Le Chatelier's principle, right? And Le Chatelier's principle says if you add a reactant, it should go towards the product side. You add a product, it should go with the reactant side. Why does that happen? It has to balance out. What's that? Okay, it balances out, but the question is, why does it balance out? It's more stable. No, that's not it. Sorry. Nice try.
As the products increase,
Gives it a chance of more reacting, right? So if you add something, more reactants, there's more of a chance of things reacting on this side so that it shifts to the right. And if you add stuff on this side, there's more chance of these things coming together and shifting back to the left. So the concentration really determines how frequently these molecules have a chance of coming together and forming either product or reactant. So if a reaction, you start a reaction and it's all A and B at the beginning, right? This is not an equilibrium, because if it's all A and B in the beginning, because you can start with all A and B, there's no C and D that's coming back, because it doesn't get formed until A and B react. As the reaction proceeds towards equilibrium, A and B, what happens to their concentrations? They go down, right? And then they get lonely because there's fewer chances for the molecules to actually run into another molecule to react with. And at the same time, these two molecules, the populations of these molecules are doing what? Increasing. So the rate of the reaction in the reverse starts to pick up. And at some point, the rate in the forward and the reverse reaction balance, and we hit equilibrium. Okay? Yeah, good. Sorry, that's kind of a long review of that. I'm going to skip this. I just said it. So this is the summary. As A and B decrease, collisions between A and C occur less often. As C and D increase, collisions between C and D will occur more often. The more often C and D collide, the more often there will be molecules that can go backwards over the activation energy curve, and that rate increases, and eventually you hit equilibrium. I don't care about these diagrams, so I'm skipping them. Sorry. Okay, so this is the equation that is important to kind of understand how it works. But I just really wanted to show you this so you remember that if I have a delta G, I can calculate a K. Or if I have a K, I can calculate a delta G. And so what they did, which I think is kind of neat, they took a table like this and they made it where they took the equation for different equilibrium constants, okay, and looked at how much free energy there would be and for the difference in the products and reactants at equilibrium. So if the equilibrium constant is 10 to the third, it's 1,000. Okay? At equilibrium, you would have the products be 99.9% of the reaction mixture. So 0.1% is the reactants. Basically, that's as good as you get. It's mostly product. But the free energy, look at it's not that much free energy. It's 17 kilojoules per mole. When we talk delta H's and delta G's, a lot of times we're talking hundreds of kilojoules per mole, right? If the equilibrium constant's 100, now you have 99% product, 1% reactant. Delta G is only 11, and then 6 for 10 to 1, and that's still 90%. Like worst case scenario in the labs we do, it might be that. But then we use Le Chatelier's principle and we shove it to the right. Like, for example, in the acetaminophen lab. Oh, not the acetaminophen lab, the isopentyl acetate lab. You took isopentyl alcohol and you added acetic acid to it. And you added a catalyst, which was an acid. Doesn't really matter which one. And you form isopentyl acetate. Plus water is floating out here somewhere. Now this equilibrium constant is more like this one. Delta G is pretty close to 0. Okay? You have two reactants, you have two products. You're breaking a sigma bond here. Actually, you're breaking two sigma bonds here. You're making two sigma bonds over there. It's kind of the same thing. They're both CO bonds. Basically the same energy left and right, same entropy left and right. Equilibrium constant is very close to 0. And yet we got a lot of product out. How do we get a lot of product out? It's just add more acetic acid because it's really cheap. Right? And it's easy to get rid of because you can neutralize it with baking soda, not sodium hydroxide, and extract it from the mixture. Okay, so we use a Chatelier's. In situations like these, we can still do these reactions in organic chemistry when you have free energies of 0 or 6 or 7 or 8 or whatever positive value you have. You just use the Chatelier's principle to shove it all the way to the right. The other nice trick that people will do is if the product has lower boiling point, they just distill the product out and remove it from the mixture and force the equilibrium to go to the right. Okay, so we're going to talk about kinetics now. Let's list the factors. By the way, this is, I don't know, they thought this was really funny, but diamonds, all diamonds will eventually become graphite. My wife found that not funny at all. So kinetics. It's how fast. It's really humid in here today, huh? What does it depend on? Concentration. Why? I don't know, because that's what he said before.
Well, because the more highly concentrated, the more possibilities it has to collide, right?
Yeah. Has to do with more collisions. Or collisions, I'll do that. Because you can have more or less depending on if the concentration goes up or down. What else? Yeah, catalyst. We'll talk about him more in a second. Catalyst, if you had a catalyst, what does it do? It makes the reaction go faster. Okay. And that's, what did you say?
It goes faster because it lowers the activation.
Lowers the activation energy. Which a lot of times is this delta, you'll see this as delta G. I had a student email me just the other night he's in a master's degree in biomedical technology or something like that. And he was like, what's that? Oh, I'm like, it's your E. He's like, oh. Like, yeah. Sorry, I get all these crazy questions like years after the fact. They suddenly remember me when they're like in trouble. Like my son sent me his research proposal for his research class, methods class, last night. So we're talking about it. And I was like, so when is this due? And he goes like, tomorrow. I'm like, that's what I thought. You're no different than my other kids. Okay, so, no, it was good though. Anyways. What else? Temperature. And there's one more thing that we usually consider, but we've kind of already said it. Activation energy. Okay. EA is usually the delta H of the reaction, and then delta G star is actually the free energy of activation. But they're for a lot of things, it's essentially the same. Okay, so when two molecules collide, do they always react? No. Why? Has to do with orientation. So they have to be in the right orientation when they collide. So in collisions, we write the rate constant of a reaction is equal to A times E to the EA over RT negative, like that. And this is the rate constant. This term has to do with the collision frequency and orientation. They call it the pre-exponential factor, and that used to always confuse me. I'm like, pre-exponential factor, that's a fancy name. What does that mean? It means it's before the exponential. Yes, exactly. But I thought I would clue you all into that secret that us chemists have. I'm easily confused by things like that. So this has to do with frequency and orientation. And this term, this is the number of molecules, I should say the fraction of molecules with E greater than EA. I thought about this the other night while I was sleeping. Thank you very much. I gave my advisor nightmares. He told me about it once. I thought it was pretty funny. So, I don't remember what it was, but I think we were just having a long conversation. Long. Okay, e to the minus x. So that's the same as what? E to the, or is that's equal to 1 over e to the x, right? And this is not one of those jokes where I end up spelling sex on the board, okay? The integral of e to the x? Never mind. You guys are too young. But yeah, you've seen that meme, right? Yeah. It's not one of those. So let's say x is large. Approaches infinity. What does that become? If this approaches e to the minus x, approaches 0. Okay. What if x is approaching 0? What's e to the 0? 1. So this is e to the minus x. That approaches 1. So that's how it actually represents the fraction of molecules from 0 to 1, because 100% would be 1. 0 would be none, right? So what happens with this? This is x. This term up here is x. If the activation energy is super high, or if T is super low, right? Not negative, but close to 0. This term gets to be really big, right? What happens to the fraction of molecules with the activation energy that are really small? It's this term here. So at the limit, the activation energy is really large. Very few molecules have enough energy to get over the activation energy barrier. But what if the temperature is really high? That's the other end of that spectrum, right? Then all the molecules will have enough energy to go over the activation energy barrier. But the ones that react are the ones that have the correct orientation. The frequency will be really high, okay? Because frequency is actually also temperature dependent, just not exponentially so they don't usually write that in. So when we look at that equation then, this is kind of a different way of thinking about it, I think. The temperature, does it affect the activation energy? No, that's a misconception, okay? But the temperature, as it goes up, changes the fraction of molecules that have energy above the activation energy barrier. When we studied this kind of stuff, actually, in let's see, I'm trying to find it. Yeah, I'm skipping a bunch of slides just to get to this slide. When we studied in gas laws, you remember we had these curves that look like this. This is energy distribution of molecules. So there's energy here, and this is the number of molecules with that energy. That at low temperature, the curve is shifted to the left, but even at a low temperature, some of the molecules have energy that's high enough to go over the activation energy barrier. So this curve is actually from like Chem 1A, and this activation energy part is what we learn in Chem 1B. This red portion is what is shown as this. Okay? And if the temperature's high enough, right, you can shove this thing all the way to the right, except there'll still be this curve always goes to 0 down here, energy. So there's always going to be some molecules that won't react. But it's the fraction of the molecules that can't react gets smaller and smaller and smaller, whereas the fraction of molecules that can react, this red portion, gets bigger. Okay? So if we increase temperature, reactions typically go faster just because there's more molecules that exceed that activation energy barrier. Okay, let's go back to the slide I was on last. Actually, it's not the slide I was on last.
Excuse me. What does the orientation mean?
Oh, okay. This is my stupid example shape. Right? If we're not oriented correctly, a reaction doesn't take place, right? So let's say you're trying to convert NO, I don't know if you can do this, plus NO to make NO2. I guess you could maybe do that. So this is bonded, and this is bonded here. Sorry, like that. And these two collide. Well, this is NO2 like this. Okay, and this is not the Lewis structure, just skeletal drawings of the two. So they actually collide like this. Then the O hits the N, and you could form the bond. But if they collide like this, then the N hits the N, then the bond can't form. You can't get that final product. You can get a different product, but you won't get that product. So the way the molecules come together, they have, when reaction takes place, molecules have to come together. If the parts that need to connect don't run into each other, right, then the reaction doesn't happen.
So what does affect this orientation?
So this is like 50-50, right? It could be one way or the other. But it can be more complicated so that only maybe 1% of the collisions come together in the proper orientation. So if you think about like biological reactions where you have multiple things that come together in different ways, for example, the terpenes, we talked about terpenes in the lab. Take isoprene units. You get two isoprene units. They have to connect at the ends and they have to run into each other and make that connection. I mean, that just doesn't happen very easily. So the fraction of molecules that come together at the proper orientation is really low unless you add a catalyst, is what biology loves to do, adds a catalyst to make things happen that don't normally happen. Okay. So yeah, if the orientation is not there,
So it's by chance.
yeah, just by chance, throwing coins up in the air, 50-50. Well, it's not even 50-50. Okay, so then, but just a little side note. So how does a catalyst actually work? Catalyst can do a couple of things, but one of the primary things it does is it takes two parts of a molecule and holds them together in the proper orientation so that the fraction of molecules that do collide, right, collide in the right order is much higher. Okay? So, yeah. We can talk more about that later. Oops. I don't know how I did that. Oh, yeah. So I want to go here. So a couple of things the book points out. This is the list the book comes up with. Concentration of reactants because of collisions. Activation energy because you have to have enough energy to make the reaction go. That is, you have to have enough energy to break and make the correct bonds. Okay. Temperature is important because it controls the fraction of molecules that have energy sufficient to go over the activation energy barrier. And then the presence of a catalyst. And actually, the fourth thing that they list on there, they call it sterics, right? If you have a bunch of things in the way of a reaction where you want two things to connect, they can't connect, okay? So big, bulky groups, we call them big, like methyl groups or things like that, that surround an area where you want a reaction to take place. If those are present, that would be sterics, and that would affect the rate of the reaction. Okay. So we have things called rate laws. And so I'm going to do a little rate law blurb here. You say rate is equal to K times then the concentration of A or something like that. Okay? That's the concentration of reactant. That's the rate constant. And that's the rate of the reaction. Now, there's all kinds of units that we use for rate of reaction, but the most common one, molarity units per second. How many moles per liter per second are reacting? Okay? But you can also see it in terms of molecules per second. Or molecules per hour. It's just a quantity divided by a time. Okay? You could do it in grams if you were so inclined. I don't know why you would, but could. Okay? Now, rate constants. Rate constants depend on this. So if this rate constant had units of 1 over seconds, then this could be molecules or molarity. Okay? Just whatever it takes to multiply these two together to give you that. So if you remember, we talked about first order, second order reactions. A first order rate law is what I wrote over there. And then K has units of 1 over time, so we'll just say seconds. Could be minutes, but just a time unit. So that when I took K times this, I would get molarity K times A comes out to be molarity units per second. But if we have a second order rate law, then rate is K times A, rate is equals K times A what? Squared? Yeah. So that means it turns out that K has to have units of 1 over molarity times seconds. And a lot of times they'll write this as moles per liter per second, and then they move the liter to the top. That's always confusing. So I just leave it like that. So that when you multiply these two together, gives you molarity units per second again. Okay? So let's say I have two reactants, A and B, and they come together to form C and D. And let's say it's first order with respect to A and 0 order with respect to B. Rate law looks like K times A to the first, and then B to the 0. And what is anything to the 0 power? 1. So this rate law that I wrote originally could apply to a problem like this. So let's say I doubled the concentration of A. What happens to the rate of the reaction? It doubles. What happens to the activation energy? Ah, nice. At least you didn't say it's more stable.
I was gonna say it's at equilibrium.
Yeah. It's at equilibrium, the sun. Yeah, the sun is the answer to everything.
Exactly.
I will bring a guitar in and we'll all sing the Mr. Sun song. Mr. Sun, Sun, Mr. Golden Sun. Sorry. You have a lot of kids, you got to do something cheap for entertainment. Okay. So what if I doubled the concentration of B? Nothing, because it's zero order in B. Okay. Well, what does that mean then about the reaction? It's all dependent on something having to do with A in terms of how fast it goes. B is important. It's a component of the reaction. But you guys remember this term rate determining step? It's not part of the rate determining step. It's not part of the slowest step in the reaction. If B were part of the slowest step in the process, then you would have seen it in the rate law. Okay? Now, how do we get these rate laws? They're all experimental. You know, it's kind of like string theory. You just make it up until you find something that fits the theory. It doesn't mean anything until then. So in rate laws, you could derive as many rate laws as you want. They're all beautiful. Biochemists are the kings of rate laws. They have all kinds of cool names like ping pong. Yeah. You can look it up, ping pong reaction mechanisms, biochemistry. Because one molecule goes back and forth between two substrates. So it's called ping pong. I don't know, I don't make these things up. Biochemists, they're clever guys. So, now, let's look at this one. First order with respect to A, first order with respect to B. So rate is equal to K times what? A to the, and B to the, and if I double A, rate doubles. If I double B, then rate doubles. If I double both, yeah, then rate is 2 times 2. It's both of them, right? It's 4 times faster. So what we say is it's first order in A, first order in B, and what's the other term we use? You guys remember? Second order overall. It behaves, if I double everything, right, it behaves as a second order reaction. So it's second order overall. We do see these kinds of things frequently when we do gases, because when you have a gas, you can just change the volume and then you change the concentrations of everything. So you could double the concentrations of everything in a gas reaction just by having the volume. Oh gosh, I go on and on for this, but these are good because you need to see these. Rate, okay. Second order with respect to A and first order with respect to B. So I'm not going to write anything up there. What would the rate law look like? Rate is equal to K times A squared times B to the first. So if I doubled A, what happens? Quadruples. If I double B, what happens? Doubles. If I double both, 8 times. Octuples? Yeah, sounds right, huh? I wouldn't use it. I would just say be 8 times faster. I don't know why we don't say octuples, but we don't. So, yeah, so first order in B, second order in A, overall. A plus B orders, 3, right? Third order overall. So if I double it, everything, it'll be 8 times faster. So 2 times 2 times 2, 2 to the third. Okay, so, hang on, I'm going to skip through some of this stuff. Oops, I don't know what happened there. Wow, I accidentally dragged through my entire presentation. Oh, I hope you guys had a good weekend, by the way. Studied, right? Yeah.
I have 4 tests
Sorry.
this week. I have to.
But at least out of your 4 instructors, I said, sorry, you have 4 tests this week. So, yeah.
I know one of my instructors is doing it too.
What? Crazy person.
He is.
Who is it?
He's a computer teacher.
Yeah.
I'm forced to.
Yeah, I have to send him a thank you note. So, Mark?
Yeah.
Yeah, I know. I'm going to send him an email. That's awesome. 2 tests on the same week. By the way, he owns an underground garden. You know that 4-HDR underground garden? That's his family, yeah.
Crazy.
So if he gives you too many tests, that's where you'll find him, right? Hiding in his underground garden.
Might have burned down his family business.
Yeah, except for it's in the ground already, so it's like,
There's holes that let air in.
yeah. Wow, you got us all figured out already. We do have people who are crib majors in here, I'm just saying. Okay, so just real quickly, activation energy. We kind of beat this one. I was going to say to death, but I don't want to go there. So, why does the lower activation energy mean a faster reaction?
With less energy to get over the hump.
Yeah, well, if the temperature's the same, just think about it, the temperature's the same, you have the larger fraction of molecules that can go over the activation energy barrier, okay? And if you want to make more go over the activation energy barrier, you can heat them up as well, So I'm going to skip the thing on sterics. We'll cover that more when we get to it in the next section. Or next lecture, I should say, which is next week. How might the presence of a catalyst affect reaction rate? So they give you one possibility here. That is, you have reactants and products, all right? And what did he do in that diagram? Lowered the energy, and then it made 3 humps, right? What do these humps represent? Do you remember what these values represent? Transition states and intermediates. That's a general term. Okay, so what happens in the reaction, the way a catalyst works, is it provides a lower energy pathway to the products. So that's, by lowering the activation energy of a reaction, it makes a reaction faster, and the way it normally does it is it breaks it up into smaller, more manageable energy steps, right? So how does that affect the equilibrium of the reaction? It doesn't.
That's what I said.
Yes, exactly. It doesn't. Why?
I'm still working that part out.
What determines equilibrium?
The concentration.
No.
What? Products in the reactant.
Products and the reactants, but what about the products and the reactants?
The forward rate equaling the backward rate.
I'm looking for a much simpler answer right now.
Their concentration.
Concentration's part of it, but just a more general answer. What determines how much
Collision.
the value of K? Free energy. Okay. Oh, you said delta G? Oh, sorry, you're right. So, I didn't hear it. So, yeah. Delta G. And on this diagram, delta G is just this. So it doesn't matter what the humps are. Free energy is just this difference between reactants and products. And so that's what determines equilibrium. Catalyst just gets you there faster. Gets you to your products in a much quicker fashion, okay? Okay, so when we think about reactions, we think about them in 2 ways then. We think about reaction rates, and that's the activation energy, or delta G with a key on it, all right? Or we think about equilibrium. So if you run a reaction, okay, those 2 things are always or can be in competition with each other, but they're always factors in determining the product. So let's take a look at this reaction diagram and talk about what product you expect to get. Okay, so now we have a reaction of A and B, and there's actually two sets of products. And this is where a lot of our impurities come from in our organic reactions. We produce what we call side products. Side products are things you don't want. Two molecules coming together in the wrong orientation, giving you the wrong product, or reacting at the wrong places on the molecule to give you the quote-unquote wrong product. It's only the wrong product because you don't want it, right? It is a product. So you can get E and F, or you can get C or D, C and D. Which one is going to form faster? C and D. So what we would say is that C and D are the kinetically favored products or the kinetic products. I'm going to see if I can write on this screen with my fat finger. I forgot my fancy stylus. What's that? So this is the kinetic product. Ooh, look at that. And it's a kinetic product because EA, C activation energy, is lower. Okay. Now, which one at equilibrium will you have more product of? Yeah, EF or C and D? C and D, right? Why?
The products are lower.
They're lower in energy.
Yeah, than the reactive.
You could have thrown the sun out on this.
Oh, I
More
was
stable first.
Oh, dang. Yeah, they're more stable. The products are lower in free energy. The lower free energy product, the difference in delta G is going to be larger. At equilibrium constant will be larger, so you'll get more of that product. So at equilibrium, you would get more in C and D, both kinetically and thermodynamically. So we have two ways of describing these. This is the kinetic product, and it is the thermodynamic product. All right, I'm going to run out of space. There. Thermodynamic. Okay. What if you run this reaction and the temperature is low? What's that going to do? Like if I have both E and F and C and D being formed, as I lower the temperature, which reaction pathway will I favor? C and D. Because E and F, remember, is exponentially dependent on temperature, right? So, yeah, so the lower activation energy will be favored at lower temperature. But if I increase the temperature, then what happens is both reactions get exponentially faster until, remember that fraction we're calculating? Both of them hit 1, and they're both going as fast as they can go. And so what will end up happening is if you run it at a really high temperature, there's a chance that you can get a lot more E and F than if you run it at a low temperature. So here's the different. Which one of these is thermodynamically favored? What does thermodynamically favored mean? At equilibrium, there's more. Okay? So which one am I going to have more of at equilibrium? C and D. And which one's going to form faster? E and F. So that's my kinetic. Well, writing with my finger works pretty good. It feels weird, though. So, in this situation at low temperature, what do you expect to get most of? E and F, because it's going to form faster. Okay? So at low temperature, you get the kinetic product. But then as you increase temperature, you're going to get more C and D. And here's the tricky thing. Remember, these are reversible reactions. And we talk about equilibrium, they go forward and backwards. So if you add enough energy that the reaction not only is going that way, but is going that way, you can form from E and F, you can go back to A and B at high temperature, and then guess what happens? C and D gets favored again because it's lower in energy. Eventually, you can take all your what's called kinetic product and convert it into a thermodynamic product. And that can be a good thing if that's what you want. It can be a bad thing if you don't want that. Okay?
So it's kind of like the, I think it was the isobenzyl lab, where we had to put the sodium bicarbonate, you had to dissolve it, and then you couldn't leave it for too long.
Or it would hydrolyze.
Yeah.
And you had this reaction. Thermodynamically, the one product you're driving, if you have that stuff in there, it drives it back to the reactants eventually because you have so much of the base present. Yeah. So it's reversing, going back on itself. The mechanism's a little different, but that's the same idea. Okay, so transition states versus intermediates. So a transition state is something that exists just while it's going through the process. It's a transition, okay? So for example, if I have I'll actually do this. I'll actually give you a real example. CH3I, and I'm adding, let's say, Cl minus to it. The reaction product is CH3Cl plus I minus. This is known as a substitution reaction. Why is it called a substitution reaction? Because I'm substituting one thing for another. That's all I'm doing. The way this reaction happens, or can happen, is this. Here's my hydrogens. And then I have an iodine here. Now, iodine is a very stable base. That's why it makes such strong acids. So it's a very good leaving group. That is, it can leave very easily. Cl has pairs of electrons. It literally kicks this thing off. And then you end up with actually the molecule with the chlorine attached to the other side. So now the hydrogens are like this, and the chlorine is connected to there. You end up like that. So this is known as a one-step mechanism. Happens all at once, okay? From reactants to products. As you go from here to here, okay? You notice how all the hydrogens are on one side and then they move to the other side? In between here, what ends up happening is this. And we usually draw these as dashed lines. That shows that one bond is forming while the other bond is breaking. That's really unstable, okay? That you have two things, and there's a partial negative charge here and a partial negative charge here. Okay, because of this instability, transition states are almost never isolated. Okay, it's always lower in energy to be either before this stage like this or after this stage like this. So if you look at a diagram like this, it's telling there's three different transition states. The transition states are unstable. They're in transition from one step to another. And then the highest points on the activation energy diagram. And then in between those, we have intermediates. So the intermediates are here. These are often stable enough that you can isolate them. Okay, so now, let's take another example of a reaction. CH3, 3Ci plus Cl minus. I'll end up with CH3, 3C Cl plus I minus. What kind of reaction is this? It's a substitution reaction. I'm just replacing one thing with another. In this reaction, the mechanism goes like this. This bond breaks heterolytically, and I end up with this. Now, is that the product? No. It actually has to go through one more step where that carbocation picks up the chlorine to form the product. These are the intermediates. There's a transition break that has to break this bond that's high in energy, because you got to break a bond, so you have to go way up there. Once the bond forms, it rearranges into a more stable, this is an sp2 carbon, so it's flat, so these methyl groups get to spread out. Okay, this is a more stable intermediate, what we call it. That's one of these things. Okay, so there's transition states on either side. That's what produces the intermediate. And they're stable enough that if you wanted to capture them, you could capture them. How do you think you could capture it? What's that?
By slowing the reaction down.
You slow it down. Slow the reactions down. How do you slow the reactions down? Remove a catalyst if it's there, or
Removing some reaction.
what? Make it lower the temperature. Right? Temperature slows down all reaction rates, so they take these reactions, they drop them in dry ice and acetone or something that's like minus 70 degrees Celsius, and the reactions just slow down enough that you can isolate these individual things and see them by spectroscopy.
If the intermediates make it more stable, then why does it go from intermediate back to transition? Why does it go from stable to unstable?
Because those are not final products, I guess. If they were stable enough that they were actually final products in the reaction, then you could have it would be a whole different thing. That would be a one-step reaction that produces product. But it's an unstable product that overall, over time, will eventually produce the stable product that's down here that you can isolate. So it's kind of a in-between two stages of a reaction. Last thing, and then I'm done, I believe. I'll let you read nucleophiles and electrophiles for fun. Is Hammond's postulate. Okay, so here's a, this is diagram's wrong, by the way. What's wrong with that statement and that?
Should be extra.
Should be exergonic, right? Lower free energy. Endergonic, right? All Hammond said, and it made him famous, amongst other things that he did, really, but he said the transition state, if you want to know what the transition state is, it's going to look like the thing that is closest in energy to. So if you have a one-step reaction, that is, there's a single hump for reactants and products, right? It's close exergonic reactions that go down in free energy. The reactants will always resemble the transition states. But in an endergonic reaction, where the product is higher in energy for a single-step reaction, these two are closer in energy, so the transition state will look more like the products. Okay? So why is that important? Because the transition state energy and like what products can form are dependent on their stability, and if you know what the product looks like, you know what the transition state looks like in the right side, and so you can make predictions about reaction mechanism. And if it looks more like the left, then you can say, well, then it looks like the reactants, and then again, you can make predictions about reaction mechanism and how things take place based on stability. Okay? Can't really say much more about it than that. Make sure you look at these slides. This is essentially a repeat of what we've said before. And I'll just sort of remind you, you need to know this stuff. An electrophile, what? Likes electrons. Best electrophiles have a positive charge and an orbital where you can place things. Okay? And nucleophiles, best nucleophiles have electrons to give, lone pairs, and have a negative charge because they're attracted to the positive nucleus. Okay? So please review those things, know them. Good.